over is Griffiths 2.2.3, the applications of Gauss's law. We introduced Gauss's law before as being the integral of all of the flux of an electric field going through some surface is equal to 1 over epsilon naught times the charge enclosed by that surface. Okay, we're going to go through a couple examples together. First, we're going to do example 2.3, and then example 2.4, which will be a different geometry. Okay, so example 2.3 asks for the field outside of a uniformly charged solid sphere of radius r and total charge q. Okay, first rule is to draw a problem. Okay, so I'm being asked for the field outside of a solid sphere of radius r. It doesn't specify where, so I'm going to make my life easy, and I'm going to put that sphere at the center of my origin. All right, so that's my sphere. It has radius r, total charge q, and I want to know what my field is outside of my sphere. All right, and I'm going to use Gauss's law to tackle that problem. All right, so I'm going to go ahead and rewrite Gauss's law. I have E dot dA is equal to 1 over epsilon naught Q enclosed. So to use Gauss's law, I need to draw a Gaussian surface. All right, a Gaussian surface is going to be any surface that encloses my total charge. I can draw any surface I want, but there's going to be a particular surface that's going to exploit the symmetry of the problem that will make my life significantly easier, and that is the Gaussian surface of a sphere. So I'm going to draw a sphere that surrounds my charged sphere. This is my Gaussian sphere, radius r. And I'm going to evaluate the left side of that integral for my Gaussian surface. So I have the integral of my electric field dotted with some patch on my Gaussian surface. All right, remember that was r squared sine theta d theta d phi in the r hat direction. And the right side of my integral is 1 over epsilon naught. And Q enclosed, what's the total Q enclosed by my Gaussian sphere? My Gaussian sphere encloses the entire solid sphere of radius capital R and charge little q, so that becomes Q, right? Because my Gaussian surface encloses all of that charge. Now, what direction does the electric field point relative to my Gaussian sphere, relative to r hat direction? Well, I chose a sphere to make that dot product really easy. The electric field points in the r hat direction. So that dot product becomes 1. And I'm left with the magnitude of that electric field times r squared sine theta d phi. I wrote this term in red up here to signify that that term comes from the geometry of the Gaussian sphere. Okay. Now, another thing that's really awesome about this is that the electric field magnitude, right? The magnitude comes from the fact that it took the dot product, right? That dot product removed, the dot product, it was E, this vector, this electric field was E in the r hat direction. Right, I took the dot product, I got the magnitude out. Now what about that magnitude and my changing positions along my sphere? Well, the magnitude of my electric field is constant everywhere along that surface. For a given Gaussian sphere, that magnitude is constant, right? We talked about drawing electric field lines before for something like a point charge. At every point along some radius away, that electric field magnitude is constant. So because it's constant, it can pull out of that integral. I'll remove the bars because we're talking about magnitudes. And I'm left with the integral of r squared sine theta d phi. Right. Talked about solid angles before. R squared is constant here. R has to do with my radius of my Gaussian sphere. And I'm left with the integral of sine theta d phi, which is 4 pi. So E r squared 4 pi 1 over epsilon naught q. I rewrite that. That was my electric field. 1 over 4 pi epsilon naught q over r squared, which is exactly what we had previous to this. Right? This is the electric field from a point charge, right? But now this point charge comes from the fact that we have some sphere of charge q. All right, I don't have a direction associated with that electric field yet. All right, but I defined that electric field already to be pointing in the r hat direction. So at the end, I make this post hoc adjustment and say, all right, well, I assumed based on symmetry that was in the r hat direction. So I have no choice but to make that consistent in the end. Right. What's pretty cool about this is that I have an electric field at some point in space. I'll draw that with red to be consistent with above. Everywhere at that point in space, I have an electric field. But I have no idea if that electric field came from my solid sphere with total charge q, or perhaps, let's do another color, a point charge of charge q. Right? This electric field can't tell you the details of the distribution of charges within the sphere. It just tells you what the electric field is at a particular point in space. I'll do the next example in another video.